Welcome to chapter 12.5. Here we discuss what is known as the tangent line problem. So, what is the tangent line problem? Our goal in this section is to find the slope of the tangent line. Well, here I have some function f of x, and in green I have a tangent line. You might recall from your geometry days that tangent lines are lines that are going to skim right along the edge of the curve, and they intersect at one point, all right? And notice that the slope of this tangent line would actually be the slope of the graph of our function f of x at the point where they intersect. So that's what we're trying to find. We're trying to come up with a function that gives us the slope of this tangent line. Now, it is possible to approximate the slope of the tangent line by finding the slope of the secant line. We talked about slopes of secant lines at the beginning of the year. Another word for the slope of the secant line is the average rate of change on the interval. That's just the slope between 2 points of intersection of our curve. So here in red, I have a secant line. Notice that this secant line is going to intersect our curve at 2 different points. And we don't necessarily know these intersection points, but we could call one of them the x-coordinate. We could call this x-coordinate x, and the corresponding y would be f of x, meaning that this first intersection point would be the ordered pair x comma f of x. And then we could travel some distance h to the right of x, bringing us to another x-coordinate that we could call x plus h, and the corresponding y-coordinate would therefore be f of x plus h. Well, as you guys know, to find the slope between 2 points, we take the change in y over the change in x. y2 minus y1 over x2 minus x1. Well, this right here, this is y2. This right here, this is y1. And this is x2 minus x1. So that gives us the slope of the secant line is equal to f of x plus h minus f of x divided by x plus h minus x. And when we simplify our denominator here, notice I have an x minus an x. Those are going to subtract to 0. We are left with f of x plus h minus f of x all divided by h. And hopefully this looks familiar to you guys, right? We talked about this earlier on in the year. This was known as the difference quotient, all right? The difference quotient, f of x plus h minus f of x all divided by h. And we did a lot of simplifying of difference quotients back in chapter 1. Okay, so that would be an approximation. So this difference quotient gives us the slope of the red line, which is an approximation of the slope of our tangent line, the green line. And to be honest, the slope of this red line, well, that's actually a pretty bad approximation of the slope of the green line, right? They're not really close to each other. However, we can make the approximation better, right? To make the approximation better, we can make h smaller and smaller and smaller. In other words, the gap in between these two values of x, we decrease it. Take a look at what happens when we make h smaller. If I make h smaller, now the slope of the secant line, the slope of the red line, is much closer to the slope of the green line. Let's see that one more time. We started here, we made h smaller, and the slope of the red line got a lot closer to the slope of the green line. Well, let's make h smaller again. We make h even smaller, and the slope of that red line gets closer and closer and closer to the slope of the green line. This would be a much, much, much better approximation of the slope of the tangent line. Well, what we should recognize here is that as h approaches 0, again, h is the distance between these 2 points along the x-axis, as h approaches 0, the slope of the secant line approaches the slope of the tangent line. This means if we want to get the slope of the tangent line, we can do so by taking the limit as h approaches 0 of our difference quotient. The slope of the tangent line is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. We take the limit as h approaches 0 of our difference quotient, and that will actually give us the slope of the tangent line. All right, this is a very, very, very important concept to recognize, and this has a special name. This is known as our derivative. The definition of the derivative. The derivative of a function f is the function f with an apostrophe. We say this is f prime of x. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. All right, so this formula will give us our derivative function. Okay, it is important to recognize this formula gives the derivative function, and this function gives us the slope of the tangent line as a function of the variable x. All right, we said this gives us, we take the limit as h approaches 0 of our difference quotient, we are going to get the slope of our tangent line. Now, the slope of the tangent line at a particular value of x is also known as the instantaneous rate of change of the function, abbreviated the IROC, at that point. We'll talk about finding the instantaneous rate of change at a particular point, the slope of the tangent line at a particular point, in some examples coming up. But recognize that this formula gives us our derivative function, and the derivative function will give us the slope of the tangent line for any particular value of x. So, when you hear the word derivative, think slope of the tangent line. Slope of the tangent line, synonymous with instantaneous rate of change. All three of these mean the exact same thing, right? Derivatives tell us the slope of the tangent line or the instantaneous rate of change of our function. Let's look at a couple examples where we use the definition of the derivative to find our derivative function. Find the derivative using the definition of the derivative. Well, what's the definition of the derivative? F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. So we need to begin setting up this equation. We have f prime of x equals, do not forget, the limit as h approaches 0. This is so important. If you don't evaluate this limit, you are not finding a derivative. We have the limit as h approaches 0 of f of x plus h. Well, what is f of x plus h? Here is my function f of x. If I'm going to evaluate f of x plus h, I replace every single x with an x plus h. Therefore, f of x plus h is going to be equal to 3 times the quantity x plus h plus 2. Right? Whatever we see inside of these parentheses, we substitute it in for x. You might recall earlier on in the year we did something like this, f of smiley face, right? What's f of smiley face? Whatever we see in the parentheses, we plug that in for x. We would plug in 3 times smiley face plus 2. All right, 3 times smiley face plus 2, yes? Therefore, f of x plus h is 3 times x plus h plus 2. Then we need to subtract f of x and take all of that and divide by h. So we have f prime of x is equal to the limit as h approaches 0 of 3 times x plus h plus 2. Notice this is the quantity, f of x plus h, minus 3x plus 2. 3x plus 2 is the quantity f of x, right? F of x is equal to 3x plus 2, and we need to now divide by h. So, to find the derivative, we just need to simplify and evaluate this limit. Let's begin to do some algebra. We can begin by distributing this 3 and distributing the negative into each term for f of x. This gives us 3x plus 3h plus 2 minus 3x minus 2 divided by h. And when we do these problems, you guys should definitely see terms begin to cancel out. Notice 3x minus 3x. Well, those are going to subtract to 0. Plus 2 minus 2. Those also give me 0. And now we have the limit as h approaches 0 of 3h divided by h. Well, you guys all know how to evaluate limits. The very first thing we try is direct substitution. And direct substitution gives us the indeterminate form 0 over 0. But the good news is that we have a common factor of h that we can divide out. That leaves us now with the limit as h approaches 0 of 3, and the limit of any constant is equal to that constant. So our answer here is 3. F prime of x is equal to 3. The derivative function in this case is equal to 3. This function gives us the slope of the tangent line for any particular value of x, the slope of the tangent line of our function f of x. All right, the derivative function gives the slope of the line that is tangent to the graph of f of x for any value of x. And hopefully this makes sense, right? We're getting a constant function. Well, let's look at our original function. The original function was a linear function. What's the slope of this line? No matter where we are on the line, it's always equal to 3. Therefore, our derivative must always equal 3, right? The derivative is a constant function as the slope of the graph of f of x is always 3 in this case. Let's look at finding another derivative. Find the derivative using the definition of the derivative. G of x is equal to 1 over x minus 5. In this case, the only thing that changes is that instead of f prime of x, we now have g prime of x, g with an apostrophe. That's going to be our derivative of the function g, is equal to the limit as h approaches 0 of g of x plus h minus g of x all divided by h. So we start off by writing down g prime of x equals the limit as h approaches 0. Don't forget your limit. Very, very, very important. And then we have to identify what g of x plus h is. G of x plus h. That means I'm going to take my function g, and wherever I see an x, I am going to replace it with an x plus h. That would be 1 over x plus h minus 5. Notice I replace this x with an x plus h. Minus g of x. Well, that's just the original function, minus 1 over x minus 5, all divided by h. G prime of x equals the limit as h approaches 0 of 1 divided by x plus h minus 5 minus 1 over x minus 5 divided by h. And to find our derivative, we need to simplify and evaluate the limit. Well, take a look. If we try our direct substitution at this point, meaning we plug in 0 for h, if I plug in 0 for h, I get 1 over x minus 5 minus 1 over x minus 5. Notice those would be the same and give me 0 in the numerator and 0 in the denominator. As we know, 0 divided by 0, the indeterminate form. And in this case, to evaluate our limit, we need to simplify this complex fraction. Yes, we've got fractions inside of fractions. So let's go back to those skills that we learned earlier on in the chapter. Simplifying complex fractions. We need to combine the fractions in the numerator by getting a common denominator. I would multiply this first fraction by x minus 5 over x minus 5, right? That's the denominator of my other fraction. And I would multiply the second fraction by x plus h minus 5 divided by x plus h minus 5. So that will allow me to get a common denominator between terms in the numerator, so I can subtract them. And then I also want to rewrite this division by h as multiplying by the reciprocal. Dividing by h is the same thing as multiplying by 1 over h. And doing out that algebra gives me x minus 5, notice that would be the numerator of my first fraction, minus the quantity x plus h minus 5, that would be the new numerator of the second fraction, all divided by our common denominator, x plus h minus 5 times x minus 5, that's the common denominator here. And again, we rewrite dividing by h as multiplying by 1 over h. Let's now do some algebra to simplify. X minus x, those are going to divide out. Not divide out, subtract to 0. Negative 5 minus a negative 5. Subtracting a negative is the same as adding. Those add to 0. And don't forget here, we need to distribute this negative to this h right here, leaving us with the limit as h approaches 0 of negative h divided by x plus h minus 5 times x minus 5 times h. Now again, if we try our direct substitution and plug in 0 for h, we still end up with 0 over 0, the indeterminate form. But notice we have a common factor of h and h, which we can divide out. In this case, it leaves us with a negative 1 in the numerator. We have the limit as h approaches 0 of negative 1 divided by x plus h minus 5 times x minus 5. We can now evaluate this limit by plugging in 0 for h. Notice we're taking the limit as h approaches 0. And if I plug in 0 for h, I get negative 1 over x minus 5 times x minus 5, or negative 1 over x minus 5 quantity squared. Here is our derivative function. G prime of x is equal to negative 1 divided by x minus 5 quantity squared. So there you have finding derivatives using the definition of the derivative. Yes, you're going to have to go back and use those skills that we learned for evaluating limits earlier on in the chapter. Look for opportunities to divide out, rationalize, and simplify complex fractions.